Welcome in. So in two-dimensional kinematics, you're going to be running into projectile motion. So what is this projectile motion all about? Well, it does deal with two dimensions. So what you have learned in one dimension and everything to do with your displacements, your velocities, your accelerations in one dimension does extend into two dimension, except now you're going to be breaking it down into both a vertical component and then a horizontal component. So a y component and a horizontal component, or you can think about even with the fact of taking something and then breaking it down into those two pieces, the x and the y. So kind of up and down and left and right, okay, if you were thinking about the directions. Well, so in here, so what you see, okay, is a little funny cannon. So you can imagine, if this cannon is on the ground and you shoot out this cannon, so typically, what might happen is you're going to be shooting this out at a particular velocity and a certain angle. So this is going to be some velocity. It's going to have a direction. It's going to be shooting this thing out. And what's going to happen with this cannon, it's going to kind of go all the way along, and then, eventually it's going to fall all the way back down. So this motion, okay, that I have just now kind of projected out is the projectile motion. So it is what happens, okay, when you not necessarily just shoot a cannon out, okay, but instead, so maybe you are jumping, okay, so as you jump and you go through, maybe you're throwing a ball, whatever it is that you have. And you will notice that it is actually in two dimensions. It's going to be going up, well, depending on what angle, okay, the velocity makes with the ground. And then it's going to be coming down, okay, so it's going to be both vertical and horizontal as you have it. So vertical and horizontal in terms of its movement. And now you want to be able to track it. So if you're thinking about something like this, and I just want to do this as an introduction, so we'll just concentrate on one item here, just so that you kind of know how to break this thing down. So if you do have, and I'm going to just kind of assume, okay, so here's my vector, and this particular vector, so what you would have is it's going to be, or make a certain angle, okay, with the particular ground. We'll call that angle theta that you have in there, and this is the vector v, okay, that you have. And notice that that particular cannonball, okay, that you will have both a vertical and a horizontal direction. Well, we know how to break down a vector into its vertical and horizontal components, so it's x and y components. I can put up a link up above there if you've forgotten it. Now it's going to come extremely handy, because that's exactly what we will want to do. We're going to have an x component, okay, of the actual cannonball, and we're going to have a y component of the cannonball, or whatever it is that you're projecting out, okay, and you're shooting out there, okay, or maybe you're jumping across. So what would that mean? Well, so first of all, your actual vectors that you would have a vector component, so you would have the vector component of x in the x direction, and you also would have a vector component in the y direction of your actual velocity. Now, there are certain assumptions that we make, in particular when you get introduced to this topic, typically in your first physics class, okay, that you would have, where we're going to be making, the assumptions that really we're under kind of ideal situations, which we typically call being in a vacuum. Now, what does that mean? Well, being in a vacuum means that there is no resistance at all. And now, what kind of resistance are we talking about? Well, this is any resistance, and in particular, one of the resistances that you would have is air resistance, because there's air particles, okay, in there, but we're assuming that we're just kind of remove them. And if you think about that, when there's no air resistance, well, what happens? Well, in the vertical direction, we know that we had an acceleration, and that particular acceleration we called g, which was the acceleration due to gravity, and it was pointing downwards, so negative 9.8 if you assume that up is positive, so down would be negative. So I'm going to put the negative in there, and this is meters per second squared. And I'm going to kind of assume that we now know that it is down. okay, because of that particular negative. So we know that in the y direction, this is exactly what we have. So I'm going to take this along, and I'm going to kind of just shift it here under, okay, this, that we have this assumption. Now, what happens in the x direction? Well, when you're initially starting this, you actually assume that there is no acceleration. So whatever velocity that you have is going to be going at a constant velocity, okay, that you're moving across in the x direction. So constant velocity means that we have no acceleration at all. So our acceleration here that we have in the x direction is basically 0. So the y direction has our gravity, which is acting on our cannonball, for example. So these are the two components. Now, we can separate them and we can treat them one at a time. You can separate and see what happens in the x direction, so meaning what happens in the cannonball as it goes in the x direction, and then you can see what happens in the y direction. Now, both of them are with respect to time, but very often we sometimes graph this on an x and y axes, okay? And we want to be able to see how it actually looks like. And what it will look like, it's going to look like as a nice projectile, okay, as we would have, and it would kind of look like this. Well, this is not exactly what I wanted to be able to show, but it's kind of going to look like that. So that's what's going to happen to that cannonball. And you can imagine that this is your x direction right here, right? And then this would have been your y direction right here. So you're going upwards, okay, in that particular sense. So that's what we would have. So x and our y. And then we can tell, okay, well, starting, if we're assuming from the ground, you don't have to start that's from the ground, although your cannon probably is going to be on the ground when you shoot it out, although maybe it's a cannon from, some kind of a castle or something that's shooting out. But for the moment, let's assume that it is the ground. So that's kind of how it would look like. And that's not going to be anything surprising because this is what we would see if we would even throw a ball, okay, at a particular distance, and that's what we would have. So these are the assumptions, okay, that we would have. We have constant velocity, but here we have a constant acceleration, and it is gravity. So how do we break these components up? Well, we use our vectors. So we do have to know what angle this is being shot at, okay, so that we can get these particular components. So let's, look at a particular example, for instance. So what if, this velocity, let's say, and let's make it simple, okay? Let's maybe say that it was at 10 meters per second, and it was at an angle of 45 degrees to the horizontal. So that's what we would have there with respect to the actual horizontal that you would take a look at. So, and then you can break this down. Now, it doesn't have to be 45, it can be 10 degrees, 20 degrees, 60 degrees, whatever. If it's 90 degrees, then it's only going up in one direction. And then we don't really have an actual cannonball that's going in two directions, both x and y, because vertical would just go up. And then we would assume that it's falling down because there's no resistances, okay, at all. So it's not being shifted around in any way. So there you go, okay, so there we go in terms of trying to see this. So let's break this down into pieces, okay, and what we would have. Well, so our component, okay, Vx would have been, okay, in this case, because we're shooting it out, so it's 45 degrees, this would have been at 10 meters per second multiplied by the cos of that angle, which in this case is 45 degrees. My actual Vy component that I would have, my initial one would have been 10 multiplied by the sine of the 45, and that's just breaking down the vector into two components. So those are the velocities. And now I can treat them separately, and I can ask all kinds of interesting questions, okay, in here. So for instance, I can say, all right, well, what's the distance that it has actually traveled? Well, if it's going under constant velocity, we would use our actual equations, okay, that we have come up with before, okay, with regards to these. So this one, what you would have is, so in terms of the displacement in the x direction, this would be nothing else but simply the velocity, okay, that we would have in the x direction multiplied by the time, right? Since there is no acceleration, this is actually our equation that we would have. And so long as we know how long it has kind of drifted out there, we would know the actual distance that it would have been covering for us. Okay, so that's one thing. Now, on the other side, if we wanted to know what the distance here is, okay, in the y direction, this is a little bit trickier because we do have an acceleration. Well, if we have an acceleration, then we can kind of go back and you can think back of all of the different equations we used, right, for kinematics. And I can put up a link up above there going through those key equations. And you would find out that, well, this is nothing else but simply, your initial velocity that you would have. But our initial velocity is the velocity in the y, okay, in this case. And it would have been multiplied by your delta t. Now, we would have plus, and this would have been 1/2. Now, the acceleration we know, so this is negative 9.8, and this would have been delta t squared. Now, what you notice is, that we're missing, okay, this delta t, right? And then here we have delta t and delta t. We seem to have everything else, so long as we know what the initial velocity is, we can break these things down. Now, what else do we know? And I'm going to just concentrate here for the moment. If I was concentrating just on the y, because on the x, okay, I can't really do much there. But what I would have is, if I was going through here, I also know that what happens to this cannonball. Well, no matter how you shoot it out, right? So as you're shooting it out, notice that eventually it's going to hit its peak right here. Right? And then gravity, because gravity is pulling it down, so it's going to work against the actual velocity and it's going to start pulling it down, and eventually at this top, right? So this is the y, okay, and I guess this is at the peak, okay? So this is going to be equal to 0 here at the actual peak. Why does it equal to 0? Because eventually it stops going up. And then it's going to start coming down, of course, okay, as you're going through. And now we can find out, how long it has taken us to get to this point. Now, no matter how you shoot it, because there's no resistance in here, what you will find is that this is actually symmetrical. So as you're going across here, if I drew a line in here, so this projectile that you would have, so this, okay, and then all of this actually takes the same amount of time. So to get to this 0 point right here, okay, as you're going through here, so as it was projected out in here, so this would take, a certain amount of time to get there. And to fall down all the way back is going to take exactly the same amount of time because there's no resistance, so there's nothing else. So this is really just symmetry, okay, that we are working with projectile motion, and this is the simple projectile motion that we would have. So if we know that these two, okay, are the same, then what we can say is this. Okay, well, in that case, we know exactly that the acceleration that we have, so the average acceleration, which is nothing else but negative 9.8 meters per second squared, it is equal to, so please recall, this would have been, your V final minus your V initial, okay, all over the change in time that it has taken us. But now this change in time, I'm going to put here a little p for the peak, right? So this is when the actual projectile goes all the way around, okay, and then peaks there, and then this will come down. Now we know that this time and this time, so this little delta t peak where it reaches the peak over here, okay, is basically the same amount that it would take to make this cannonball fall down. So the entire time is going to be, twice as long. Now, can I solve for this? Well, yes, of course. So this right here is just nothing else but 0. This initial one, well, this is what the cannon has been shot out at. So for instance, for our example, what we would have is we would have negative 9.8 is equal to 0 minus, and this was just 10 times, okay, and this would have your sine times whatever angle it was shot at. Well, in this case, it was 45. And it would have been divided by the delta t and the peak. So I can solve this definitely. I can bring this delta p on the other side right here. So delta t, a little p, and this would have been nothing else but negative 10 sine of 45 degrees divided by, negative 9.8, right? So the negatives would cancel as we would have them, and we would know exactly how long this has taken us. So I can do this. So now this, of course, will depend on what we have been given in terms of the angles and the actual speed that this thing was shot out at, or you jumped at, or you threw the ball at. It's going to be 9.8, equals. So this is approximately, let's say 0 point, I'm going to put 721, 5. You can put more if you like. And this was in seconds because we are just dealing here, okay, with everything in meters and in seconds. So just make sure that you're consistent in your units. So what does this mean? Well, this means that this cannon was shot out and it reached its point, okay, at 0.7215 seconds. And now as it continues on, so the entire path, well, this would have been twice as long for that. So if we had this, we could have taken this, multiplied it by 2, and we would have known that the entire delta t was equal to 1.44, 3, and so on. You can keep as many decimals as you like, but that's the entire trip duration that we would have. So very quickly, we can obtain that. And from there, we can now get everything that we really kind of want. So if you want to know what the actual displacement was in here, we can certainly obtain that, right? Okay, so we know that the total displacement in here for the whole duration, what we want to be able to see is with the cannon as it's been shot out. So in here, this is the peak, right? So we can find out, what that height was. So that could have been, the delta dy of the peak. But what do you notice that if it comes all the way down, well, the displacement in the y was actually equal to 0, right? So this is equal to 0, and we can actually double check that in here if we substitute everything. So we now know Vy, we know this delta t, right? We know the acceleration as we substitute this in. We want to see if that displacement was equal to 0. Now you might ask yourself, wow, that's interesting. So I could have substituted here for the entire duration. I could have substituted 0. And I could have been solving this, right, for delta t. Now, you would have to solve a quadratic. So you would have to go back to grade 10 and think about, solvings of quadratics. And that's completely fine. Now, typically, students coming in to physics, for the first time, sometimes you might forget quadratics. And sometimes, depending on your background, you might not even have run into quadratics yet. So this is much easier to be able to think about this problem because here you don't have any quadratics, you're just solving for this, and it's a very easy solution to be able to find this time, to be able to find that, and then just multiply it by 2 to get the total time. So there's kind of 2 approaches that you can use in there. Now, when we have this, so sure, the displacement in the y for the whole trip would have been 0. Now, what would have been the actual displacement over here? So, how far did that ball actually go in the horizontal, okay? So from where it has been shot, okay, all the way towards the end. Well, now that we have delta t and we have Vx, we can certainly find this out. So this would have been nothing else but 10, cos of whatever angle we have, multiplied by the time. Now for us it was 1.443, etc. And we can find out what that distance was. So 10 multiplied by cos of 45 and then multiplied by the time, so I'll just put that in there approximately. So this would have been launched, not very far. It would have been just 10.2 meters, for example. So that cannonball wouldn't have gotten very far, okay, at least in that particular speed. So maybe let's imagine it's a miniature cannon, okay, instead of an enormous cannon, which are definitely shot at much faster speeds than just 10 meters per second. So that's what you would have, assuming that there was no resistance. So the whole goal of this projectile motion is for you to be able to understand, okay, how to break these things down. And typically you do start with your velocity. And that velocity, depending on the angle, can be broken down into its x and its y components. You certainly know quite a lot of information. You know what happens at the peak. You know that the velocity on the vertical is 0 there. Okay, so you have that. You know that the whole displacement on the y would be 0 if you're starting from the ground. So you know that, so you can use your intuition. You know that the acceleration due to gravity is approximately 9.8 meters per second squared down. And you know that in the x component, there is no acceleration in this ideal case, which makes our problem very easy to be able to dissect. And then we can break it down into pieces. So I hope that this gives you an introductory component and a structure towards this projectile motion when you do start up your physics. This is not an easy thing, especially if you've never seen something like this where you're breaking things down into two components. But intuitively, you should understand what happens. So if you shoot something out or if you jump, you know that it's going to take on this path. And this particular path that it takes on is actually a quadratic. So sometimes students will be introduced to that. But even if you don't know it, you can visualize something being projected out, okay, and then that it travels. And both, it travels in the y, so it goes all the way up, and then it comes all the way down. And in the x, it obviously travels a certain distance. All right, so thanks for watching. Happy physics studying. We'll see you in a future video. Bye, everybody.